Hi, my name is Richard Moore, and this is my Physics 2 Lab 4, Circuits. Introduction Instructions. The instructions for this lab were to analyze the behavior of different circuits. The first of which being to evaluate the charge and energy conservation in series circuits, the second of which being to evaluate an RC circuit, observing how a capacitor charges, and the third of which to evaluate a time-dependent voltage across a discharging capacitor. In order to perform these evaluations and all steps required, the lab instruction manual was to be followed, detailing a step-by-step procedure to follow and different values to calculate. Purpose. The goal of this lab was to predict the behavior of circuits containing resistors in series and parallel, examining the behavior of ohmic resistors and capacitors. Overall, though, the purpose of this lab was to learn more about circuit behavior, a topic that has been discussed extensively in class recently. Results preview. Through this lab, the behavior of three different circuits were analyzed and quantified in relation to voltage, current, and time constant, being Circuit 1, charge and energy conservation in series circuits, Circuit 2, RC circuit, observing how a capacitor charges, and Circuit 3, time-dependent voltage across a discharging capacitor. Seen below are two images of the circuits. Models and principles. The models and principles used in this lab were resistance in series, being equal to R1 plus R2 plus Rn, Ohm's law, which is V is equal to IR, loop rule, which is the potential difference of a loop is equal to 0, node rule, which is I in is equal to I out, and the linearization equation seen below. Rationale. The resistance in series equation was used to determine the resistance in series of a circuit. The Ohm's law is used for the determination of circuit variables V, I, and R. The loop rule substantiates that delta V must be equal to 0, which is helpful in the process of measuring and determining voltages. The node rule assists in determination of current, specifically the conservation of such, and linearization is significant to the analysis of a time-dependent voltage across a discharging capacitor circuit, specifically in relation to determining RC. System and surroundings. The system in this lab was a circuit, including all components that relate to its functioning, and the surroundings was everything else near the experiment that does not include the circuit, such as tables, chairs, and any other nearby electrical objects. Initial conditions. The initial conditions for this lab can be broken into Circuit 1, Circuit 2, and Circuit 3. For Circuit 1, there are two 1.5 volt batteries, the multimeter, ammeter, voltmeter, a 47 ohm resistor, a 100 ohm resistor, and that the resistors are in series. For Circuit 2, the initial conditions are that there are batteries, a 200 mF capacitor, and two light bulbs, first being a 10 ohm and then second one being a 20 ohm. And for Circuit 3, the initial conditions are once again the presence of batteries, the 200 mF capacitor, and then a 30 ohm light bulb. Experimental data in series. For the first circuit, the expected current, according to V is equal to IR, was 0.02041 amps, and the actual measured current using the node rule was 0.01 amps. When the ammeter connection was reversed, the sign became the opposite. Voltages. For delta V net of the whole circuit is equal to 0, which is used to calculate the voltages at every point. For the true resistance, R is equal to VI, which is performed for each resistor, and when the voltmeter is replaced with an ammeter in parallel with the 100 ohm resistor, the current reading will increase due to splitting. Experimental data, RC circuit. For the battery connected to the 10 ohm light bulb and capacitor in series, the current goes to 0 and the capacitor charges. When the capacitor is directly connected to the light bulb, the current goes to 0 and the capacitor discharges. The charge and discharge times for the capacitor over the 10 ohm connected to a 10 ohm light bulb is roughly 18 seconds to charge and 16 seconds to discharge, and the charge and discharge times for the capacitor with the 20 ohm light bulb is roughly 36 second charge and 32 second discharge. Experimental data, time-dependent voltage across a discharging capacitor. Using the linearization equation seen below, the slope is equal to -1 divided by RC, and we can find RC from the slope, being roughly 9 seconds. To the right, seen there in the image, is an image of the circuit created. Potential errors. The potential errors in this lab are timing errors, inaccuracy in the circuit setup, as there are not perfect connections that could have influenced behavior, and the existence of resistance in the wires and circuitry components, including the ammeters. According to this what-if question, in a virtual experiment, the ammeter will have idealized resistance at 0, while in real life, the ammeter most likely has some resistance, affecting the behavior of the circuit in general. This rationale would then make the actual current lower than the virtually simulated current in accordance with V is equal to IR due to the inverse proportionality. And according to this what-if question, the actual experiment has a higher capacity charging time than the simulated experiment due to the unidealized reality of nature. In the virtual experiment, there is no resistance, when in reality there is, although it is minimal, and therefore increases the charging time. In conclusion, the overall behavior of three different circuits were analyzed and quantified in relation to voltage, current, and time constant, being Circuit 1, Circuit 2, and Circuit 3. And the fundamental behavior of circuits and processes of quantifying such were learned about, granting a greater comprehension on this subject. Thank you.